So hi everyone, so I'm Damien from Criteo, and I'm going to tell you about machine learning for display advertising at scale. So let's start by the outline of the talk. So I'm going to talk really briefly about the ad tech and about Criteo, just for you to understand the context of the talk. Then I'm going to deep dive into the machine learning algorithms that we use for display advertising. And then I will continue by talking about offline and online evaluation for this algorithm, and I will finish by discussing future areas of research for us. So really briefly, just for you to understand the context, so we do display advertising for performance, which means that on one hand, we buy ad space on different publishers' sites. So for example, some people, they go to the Boston Globe, they go to the New York Times, and they will be shown some ads. And so what we do is that we pay some money to these publishers so that we can show ads to people. And then when our ads, they actually drive performance to our clients, to the advertisers, then we would get money from the advertiser. So we show ads, and then if people, they click, they buy, they do something for the advertiser, they drive value, then we get money from the advertiser. So that's performance display advertising, where we take a risk and then we get rewarded when we drive performance. And so our machine learning engine in this context is trying to answer three questions. The first one is, given an ad space for like a given person at a given time on a given website like the New York Times or the Boston Globe, how much should we bid for this ad space? Then if we bid and then if we win the ad space, what products shall we show to the user? So we can show many different products. What should we show exactly? And then once we have decided this, what is the exact look and feel of the banner? So shall we show like 2 products or maybe 4, maybe more? What is the layout of the ad? What is the color of the ad? So everything is optimized using machine learning. And the common objective of all this engine is really to drive value for the advertiser. And so we do that at a large scale. So we have more than 1 billion monthly users. And so this means that we have many requests per second to decide like how much we want to bid. We win many of these auctions, so then we have many displays per second that we display. And this means that we have really a small amount of time to decide how much we want to bid. We have about 10 milliseconds to decide how much we want to bid. And then we also have a small amount of time to decide what is the exact ad we want to show to people. And this has an influence on the machine learning algorithm we can actually use because not all of them would actually make this scale. So let's now discuss the machine algorithm we use in our engine to solve these problems. So as I was saying, we have 3 questions we're answering. How much we want to bid, what products we want to display, and what is the look and feel of the banner. And so we have machine learning algorithm for these 3 questions, and they all rely on a common machine learning platform. So now I'm going to talk about the algorithm for each component, and then I will discuss the common ML platform that we use for all these models. So let's first discuss bidding. So let's imagine someone visits like the New York Times, and then we receive a bid request. How much do we want to bid for this? As we sell performance, our objective is aligned with the client's objective. So our goal is really to drive performance for the client to generate value for them. And then most of these auctions, these real-time bidding auctions, are second price, meaning that we have different people bidding. For example, let's say Criteo bids 10 cents, the second competitor bids 8 cents. Then because we are the highest competitor, the highest bidder, then we win the auction, but we don't pay our own bid, we pay the bid of the second highest competitor. So there's a difference between how much we bid and how much we actually pay when we win. And that's where you make some money, you make the difference. And so in this context, the value that we should bid is the maximum value that the client is willing to pay for the click or for the sale. And so this is the most common type of auctions. There are other types of auctions like first price auction where you pay what you bid. And in this case, we have to adjust our bid. We have to bid lower so that we can still make some money in this case. And so in this second price type of auctions, what we bid depends on the predicted performance and depends also on the objective of the campaign. So some people, they care about clicks, and in this case, we should bid the max CPC, so the max cost, the maximum amount of money the client is willing to pay for a click, times the predicted probability of click. But yeah. I really don't know. Guess, that's a tough guess. Yeah, I don't know. And then but the clients, they don't care only about clicks, they can care about conversions, about sales. In this case, we bid like the maximum CPO, the maximum amount of money they are willing to pay for a sale, times the predicted, the probability of the person actually generating a sale for the client. And then we can generate all other things like the amount of money that the person will spend and things like this. And then, so this is the bidding strategy, and then how we train this model. So we have probability of click, probability of conversion, these machine learning models, and we train them in a classical supervised learning way. So we have historical data, and we have some features, and we train models on this. And I'll go back into more details about this later. Now we bid, and then maybe we win the ad space, and then we have to decide what are the products that we want to show. So to do this, basically we have some products, and we want to recommend products to the user. And so we have a billion user, and we have 3 billion products in our catalog. So this is really big, and we want to make it scale and to keep it fresh. So one thing we can do, and that we actually do, is to pre-select products offline, and then to have a more fine-grained machine learning model to do the final scoring online. So every time we receive a request, we cannot go through the whole catalog to find the best products. So we will have some candidates that will be pre-computed and put in memcache, and then we can just score them using a machine learning model online for every request. So how we do this pre-selection offline? So we use some sources of products. So for example, we will take like the historical product that the person saw. We will take another source which will correspond to the most viewed products in the same category. And then we can use collaborative filtering to find like similar products, complementary products. So this is something we do offline frequently. Then we upload like these candidate products in memcache. And we can use a more fine-grained machine learning model to do the final selection of the products. So to do that, we also use classical supervised machine learning approach. So we have historical data. So for each product, we know like whether it was clicked, whether it led to a sale, how much money the sale corresponded to, and we can build different models depending on the objective of the campaign to solve this problem. And then the last aspect is so the look and feel optimization, where we want to find like the best layout, the best color for the ad. And for this, we also use classical supervised machine learning. So we have data about the performance of different colors in different contexts, different layouts, and we can use different features to build like a machine learning model to optimize for clicks, sales, and things like this. That's just an overview of the different models that we use to do display advertising. And I'm going to talk more about the technical details of our machine learning platforms and how we train these models at scale. So as you saw, so we have many different models. We have models for bidding, we have models for recommendation, we have models for look and feel, and then we have different objectives for the campaigns. It can be clicks, sales amount, and so we have all these models, and so we train them independently, and we try to refresh them as often as possible. And for us to have fresh models is really important. So if we don't refresh a model, let's say, in half a day, then we really start to lose money. And if we don't refresh them in 2 days, for example, if the platform doesn't work, we start losing like huge amount of money. So we really want to have something that's robust, that scales, that allows us to train models fast. And so because of these constraints, the online constraints that we have in terms of latency, so we use linear models in many places. So for example, logistic regression, when we try to predict the probability, and this really gives you state-of-the-art performance if you do it well, but it's also like really fast to evaluate and fast to train. So this is a good compromise. And so we have different types of features when we're building our models. We have features about the user, features about the advertiser, and features about the publisher. And most of them are categorical. And I'll get back to that. And so I said we have lots of data, so and our data is also really sparse. So if we have, for example, 10K displays, we will have about 50 clicks and maybe one sale. So we have lots of data, but at the same time it's really sparse. So we can take this into consideration. We can downsample the negatives and do things like this that have been discussed today already, so that we don't, so that we really take the part of the data that allows us to build good models. And then so we use linear models, so how can we get good performance using linear models? So the idea is to add interaction between features, because if you use like a really simple linear models, then you won't get very good performance. For example, you won't be able to know what is the performance of an ad for Expedia on the New York Times, or of an ad for Expedia on the Boston Globe. You won't be able to tell the difference. You would get an average over all publishers, and this is not very good. So what you do typically is that you add quadratic features, which allows you to handle the interaction between two variables, for example, the publishers and the advertiser. But then you really start to have lots of features, because you have a combinatorial explosion when you add high order terms, and then you have to have a way to deal with this. So for example, in the public dataset we released a few months ago, we had almost 1 billion unique feature value like this. And so it means that if you would just fit a machine learning model on this data, you would have 1 billion parameters. And this is really not something that you want, because it's lots of memory online, it's really long to train. And so what you do to deal with this, so here we have mostly categorical features. The standard way to do that is to use one-hot encoding. And that will lead to these billion parameters that you want to fit. And so you want to reduce this space. So one thing you could do is, for example, to remove the features that are not non-frequent in your dataset, because most of these billion features, they won't be frequent at all, so you could remove them. Another way to go about this is to use more like an automatic approach that is called the hashing trick. That was made popular by John Langford in VW. And the idea is to take your data and to hash it and to project it in a smaller dimensional space, for example, of 10 or 100 millions of parameters. And now this is good because whatever the data, you project it to a fixed size space, and then you have, let's say, 50 million parameters, and then this is fixed, whatever the data. And the drawback of this approach is that you have collisions between features. So, for example, the cross of Expedia and New York Times could be the same as the cross of Booking and Boston Globe. And then you get one parameter for these two really different contexts. But we found in our experience that this is actually a minor impact on performance, and that this actually does work really well. Then to train our model, we have our own in-house machine learning library that runs on top of Hadoop. And in most cases, we use L-BFGS initialized with SGD to train our parameters. So why do we do this? So the idea is that we really want to optimize the function well. So we really want to go as close as possible from the optimum. And SGD, which is good far away from the optimum, really takes a really long time to converge to the actual optimal value. It's really good at the beginning, but it's really slow to get you to the optimal value. On the other hand, L-BFGS is really slow at the beginning and really fast closer to the optimum. So we combine them to be really good at the beginning using SGD and really good closer to the end using L-BFGS. That's the idea. And then how do we do that at scale? So we have to distribute the computation of both algorithms. So L-BFGS is a batch algorithm, meaning that we do one pass over the data to compute the gradient and then do one step. So it's easy to distribute because you can distribute the computation of the gradient. So each machine can have a part of the data. Each machine computes its local gradient, and then you synchronize the machines to get the global gradient and do one update. On the other hand, SGD is much trickier to distribute. Because you have to do that so you do much more updates, and so you have to synchronize much more often. What we do is that we synchronize not too often, and then we do parameter averaging between nodes to get a global model. And this works well for us because we use SGD only as a warm start for L-BFGS. So even if the distribution is really approximate, we still get good performance. And then to do the distribution, we use Hadoop all reduce that was mentioned by Eric before lunch. The idea is to open TCP connections between reduce nodes. So not to do like reduce many reduce steps that will force you to spill on disk. We keep like one reduced step, so only one step with many machines, and we open TCP connection between them so that they can exchange kind of in-memory synchronization of data. So you build a tree, each machine says like its current state to its father, the father aggregates, you go till the root, and then you broadcast down the global state. So here I talked about fairly simple technique like Lucy's regression with autoregularization, but we use some more advanced techniques in some places. So we have some transfer learning, some factorization machines, learning to rank. So, but I cannot go into all these details, but if you're interested, you can come to me afterwards. Just to give you one example, so we use cost-sensitive learning for the bidding aspect. For example, when an advertiser sells many things, like maybe it sells stocks, but it also sells TVs, then we want to be able to tell them apart, like one sale, if you sell a stock or if you sell a TV, essentially the same thing. And so we kind of downweight the small sales so that we don't spend too much training on the stock, but try to evenly spread the learning so that we are good on all types of sales. So I'm going to talk briefly about offline online evaluation, and then I will continue with future areas of research. So we do the classical offline online two-step process. So offline evaluation is cheap, it's fast, it's efficient for wide exploration, and then we do online A/B tests to get the final word on any of our improvements. For online metrics, so we use the classical metrics for example, in this case for prediction models, so log likelihood, RMSE, AUC. So we use these metrics, but we found that they are not so good because they focus on the prediction power of your model, but they ignore in the context in which you use them. So we use our prediction model in the context of bidding. Maybe we get improvements in terms of likelihood. We have really better prediction models, but maybe this improvement is in situations where we don't have any competition. And in this case, getting better don't bring any value to us. And so what we do is that we've researched and publish some more advanced metrics that will model the competition and put your prediction model in the context in which they are used, so that you can see, okay, is there an improvement here or not, and you can get better offline-online correlation using these metrics that you would get with classical metrics. And then for online metrics, so as I said, we care about the value we drive for the advertiser. So we will look at this for a given cost, for a fixed cost, how much value do we bring for the advertiser, meaning how many clicks, how many sales, what sales amount. So that's really what we look at online. Then some statistics. So we run many offline tests every year. So about more than 100K, sorry, offline tests per year, and many A/B tests also. But you see, we cannot run as many A/B tests as offline tests. So it's really important that we get good offline metrics, and many people are involved into this. And we've developed machine learning, an experimental framework similar to what people from Cora were telling us in the morning, so that people from different teams can share results so we use the same testing framework for all our models, for all our experiments across all the teams, so that if someone runs an experiment and want to show it to someone else, then it's similar results, similar metrics, so it's easy to work and to collaborate. Okay, now so we work on many different things that are open areas of research. So I picked 3 ideas that I think are really important. So one of them is counterfactual evaluation. So this is how to improve your offline metrics. So I said offline metrics are important because you cannot run A/B tests for everything, and the offline metrics that you have, they are never perfect, right? The correlation offline online is can be close to 1, but it's not that close to 1. And counterfactual evaluation allows you to estimate the online metric, like clicks, sales, advertiser value, directly, from your logs offline. So it's like the result of an online A/B test, but without running the online A/B test. And the idea is to use randomization online. So when you would use your production model, you actually randomize in some situations, so that you can know how another model would have performed online if you would have used it, but without using it. So that's kind of the idea. So we have good results on clicks, but it's more difficult to do that on noisier, sparser metrics like sales or sales amount, but we're working on this. Another Another idea is to work on embedding. So we've talked about this a lot today. Embeddings like Word2Vec, so they are used in many places, and can we leverage these tools that are quite powerful to help us compute similarities between products, between users, so that's also something we're working on. And then another, the last thing I want to talk about is policy learning, which is the idea to go away from the classical supervised learning approach. So for example, if you think about optimizing colors, so what we do now is that, for example, you have few colors like blue, green, and red, and for each color you really try to know, if you predict clicks, the exact click probability of this color in this context. And that's really hard actually to know the probability of this color. When what you want to do is in fact just to find the best color. You don't care what is the exact click probability, you just want to know like red is better, because here you don't bid, you just try to find the best color. And this is a hard problem that may be overkill for what you want to do. And policy learning allows you to find the best color, optimizing an online metric. This kind of the optimization side of counterfactual optimization. And one nice thing about this is that when you don't have different choices, for example, you have only one color, you don't try to optimize, you don't try to predict the click really hard, you just say, okay, I have one choice, so I don't have any gradient, I have only one choice, so it's easy, I just pick the color I have. And to finish, just a word on academic research. So we have released a couple of online data sets over the years. One of them has 1 terabyte in size and contains quite a bunch of our traffic. And we also published some papers recently. So one of them has this utility metric at WWW last year, and also 2 papers, one of them on cost-sensitive learning I was telling you about at the NIPS workshops last December. Thank you.